Hi, I'm ready to do Module 3. Okay, I'm just going to switch to my presentation, and I'll just share this really quickly. Okay, so we'll start out with my module, and okay, so multiple regression and correlation and ANOVA. So first we're just going to talk about just like the basic differences and similarities between ANOVA and MRC. They're both under general linear modeling. We have ANOVA, which has error as random, and then we have multiple regression coefficient, which is residuals and error as interesting. Both of these measure the differences in the independent variable makes on a dependent variable, but they differ in the test they apply to the significance of that difference. So regression is predictive as well as a descriptive procedure, and it kind of questions what are the underlying relationships between/among variables. Gary King, his article says regression is simply a sample estimate of a population conditional expected value. So when we look at ANOVA here, we have our F-test and T-tests. F-test is just a simpler way to compare multiple level factors. So instead of doing a lot of T-tests and having alpha inflation, we can just do an F-test. And then for MRC over here, we have RPT, and that's a correlation between continuous and binary variables, and we can convert this into a T-test. So just important to know. Now we go on to MRC and its assumptions. The first one we're going to talk about is a linear relationship between the predictor, the x variables, and the dependent y variable, so a rectilinear relationship between x and y. So here we have standardized residuals versus unstandardized predicted values. So standardized are standardized with t-values, while unstandardized are a line of best fit values, are observed y-values. So ideally, to test this assumption, our points should be at the 0 line, at a horizontal line, and they should kind of be like distributed along this line, but as you can tell, they're kind of all over the place. So it's not an overall relationship between all of the predictors and the dependent variables, so overall linearity assumption fails. Next, we're going to look at the assumption of homoscedasticity, and that's a variability is constant across predictors. For mine, it varies a lot, so we don't have homoscedasticity, and ideally we want that. So next, we talk about the predictor is sensible for the outcome. That's our assumption number 2. So my 3 independent variables are meaning in life, affect, and family support on satisfaction with life. So we would think that high meaning in life, positive affect, and high family support would be sensible for high satisfaction with life. So we kind of fulfill that assumption. And then our third assumption is the prediction of y does not require other predictors than x. So, and looking at my data set, I'm not leaving out any variables that could significantly affect satisfaction with life. So that's the third assumption. Okay, so now we go to this one. We're measuring, assuming that there's no measurement error, and how we kind of solve for this assumption by looking at Cronbach's alpha. So we're looking at the reliability between meaning in life, affect, and family support. So our alpha is 0.531. It's not that high, not that great, so our reliability is a little shaky with that one. For the next one, we look at our mean error, or our residual equals 0. And if we go here and we see that, so that we fulfill that. If the mean residual is not 0, then we're most likely overshooting or undershooting the observed value, and we kind of don't want to do that. Okay, so next we look at multicollinearity between predictors, or among predictors, and we look at that by our significance between meaning in life, family support, and affect. And we don't really see any significant values within this, so we can assume that there isn't any multicollinearity, which is good. Next, we look at parameter estimation. So that would be our B's. And that's estimating the population parameter with sample data. So our B's are the parameter estimates of the betas. And it's a precursor to hypothesis testing. We need parameter estimates to collect information for hypothesis testing, for the t-test. So when we look at our B's here, we can, it's really for every point, 1 point increase in satisfaction in life. We have a 0.068 increase in meaning in life, a 0.268 increase in family support, and a 0.069 decrease in affect. So those are just important for our regression equation for kind of when we put back in those our numbers, and we can kind of, that just helps us look at our results or have more understanding of our results. For our R-squared value down here, it's 0.051. R squared value is a measure of the spread of the points around a regression line set by Gary King, and we want a high R squared, which mine isn't high at all because it's 0.051. So that's just something to take into account. What else? So for beta, we have our standardized coefficients. Betas are the same as correlations, but we have to remember that correlations and causation is not the same. And that we also have to understand that betas are more difficult to interpret. They don't add much info to help compare effects from different variables, and they may add misleading information. And that was taken from Gary King's article, just some things to keep in mind. Okay. And then this is just like a scatter plot of our variables, kind of a visual to show satisfaction with life, with affect, with family support, and with meaning in life, just to kind of show the spread of that. When it doesn't look very good, I mean, it's kind of like all over the place. There isn't really a clear direction or like a tight line with it. So now we're going to move on to ANOVA and its assumptions. So the first one is that you have continuous dependent variables. So my dependent variable is satisfaction with life. It's measured on a scale, so it's continuous as opposed to categorical or binary. Assumption number 2 is that you have independent observations. For mine, it's between subjects, and one person isn't in more than one factor. So that's what it means by independent observations. So we fill that. We also have, for my experiment, we have categorical. For my factors, it's categorical and 2 levels for each. It's quasi-experimental. So I have which parent are you closer with, and we have mother and father. And then where do you derive meaning in life, and that's career and relationships. So just 2 levels for each, and it's categorical. For assumption number 3, there should be no significant outliers, and that's shown in our box plots here. And you can see that there's one here, there's one for 15, I think that's a 9, and then we have one for 23. So we would go back and check at those and possibly throw them out. So just as kind of, it's messing with our data, could kind of mess with our results, like a clear results. So we would go back and look at those. For assumption 4, it's your dependent variable, your residuals, should be approximately normally distributed for each cell of the design. So we would check this with our QQ plots. And they look to be pretty close to that line of best fit. So that's really good. The purpose of a QQ plot is to test for the normality of data. And it seems it's along the line of best fit, so that seems pretty good. We can also test the normality of data with the Shapiro-Wilk test. And we want to fail to reject the null. The null hypothesis is that residuals are normally distributed. So we want residuals to not be normally distributed. So we want high p-values. And we kind of have that for 0.826, for 0.420, and for 0.609. So we have that for 3 of our factors. And then the final one with relationships, we have, it's actually significant, but for 3 of the 4, it's not. So we would reject the null for these ones. And we can look at that with our Shapiro-Wilk test. Okay, and then finally, we're just going to look at our ANOVA with 2 factors. So like I said, I looked at I looked at your closeness with parents and meaning in life and how they affect satisfaction with life. So if we're going to look at our main effect first. So closeness with parents seem to have a significant result. So we have 0.01, and that's below the 0.05 level, so that's significant. So this would mean the mean difference between the two conditions. So significant difference in satisfaction with life and the main effect of closeness with parent using mother and factor factorial levels. And then we look at meaning in life, and that's not significant. It's higher than 0.05. And we look at our interaction between closeness and meaning on satisfaction with life, and that is not significant as well. So interesting to take those into account and to kind of like test what we're trying to measure here with satisfaction with life. Okay, and that's the end of my module. Thank you for this semester, and happy holidays.